In this video, we'll explore how zirconia, or zirconium dioxide, ZrO2, has become one of the most versatile and advanced materials in modern engineering and healthcare. You'll learn how zirconia is produced, how it's shaped into strong and precise ceramic parts, and why it's used everywhere from jet engines to dental crowns. Zirconia is a high-performance ceramic derived from the natural mineral zircon. It's chemically stable, extremely hard, and has a very high melting point of over 2,700 degrees Celsius. Unlike metallic zirconium, which is ductile, zirconia is known for its toughness and resistance to wear, corrosion, and heat. The production of zirconia begins with the mining of zircon, a mineral found in heavy sand deposits like the one shown here. These sands are rich in heavy minerals, including zircon, rutile, and ilmenite. They're usually found in ancient coastal deposits, where ocean currents have naturally concentrated them over millions of years. Mining is mostly a surface operation. In Australia and South Africa, large dredges scoop up a slurry of sand and water, which is then pumped through spiral concentrators, those long, sloping tubes you can see on screen. Inside the spirals, gravity does the sorting. Heavier zircon particles move outward along the spiral's wall, while lighter quartz sand stays closer to the center. After that, magnetic separators remove unwanted iron-bearing minerals, and electrostatic separators pull out any remaining impurities. The output is a fine, clean mineral concentrate, zircon sand, that contains about 65% zirconium oxide by weight. This concentrate is dried, bagged, and shipped to refineries worldwide. What's impressive about this step is how sustainable it can be. Many mining operations recycle 90% of their processed water and return the sand to its original site, replanting vegetation once mining is complete. Once the zircon sand reaches a refinery, the next goal is to extract pure zirconium. The photo here shows part of a chlorination system, the starting point of the refining process. Chemically, zircon is zirconium silicate, a stable compound that needs to be broken down to isolate zirconium. So in the chlorination stage, zircon reacts with chlorine gas and carbon at around 900 to 1,000 degrees Celsius. This reaction produces zirconium tetrachloride, or zirconium tetrachloride, a volatile compound that vaporizes easily. The gaseous zirconium tetrachloride is then condensed into crystals and purified by fractional distillation. This is where the famous Kroll process comes in. Named after metallurgist William Kroll, it involves heating the purified zirconium tetrachloride with molten magnesium in a sealed vessel. The magnesium removes the chlorine, leaving behind spongy metallic zirconium and magnesium chloride as a byproduct. That zirconium sponge is later melted under vacuum to form ingots for metal applications, or oxidized back into ultra-pure zirconia powder for ceramics. The final but critical part of refining is separating zirconium from hafnium. These two elements are nearly twins, chemically identical, but with different neutron absorption properties. Hafnium must be almost completely removed for nuclear-grade zirconium. But for ceramics, maintaining low hafnium levels improves color uniformity and face stability. Now that we've got refined zirconia powder, the process shifts from chemistry to materials engineering. Zirconia powder is incredibly fine, almost like flour. Engineers carefully control the particle size and distribution because that consistency determines how the ceramic will behave later under heat and pressure. There are several ways to shape this powder into usable parts. The first is uniaxial pressing, where powder is compacted in a mold under tons of pressure. It's simple and fast, ideal for discs or rods. Another is injection molding, where zirconia is mixed with a binder and injected into molds, similar to how plastics are formed. Great for complex shapes like valves or dental blanks. For larger, hollow, or more intricate parts, slip casting is used. In this method, a liquid mixture of zirconia powder and water is poured into porous molds, which absorb moisture and leave behind a solid shell. Once the parts are shaped, they go through sintering. The image here shows a furnace glowing at around 1,600 to 1,700 degrees Celsius. During sintering, the individual zirconia particles fuse together, reducing porosity and forming a dense, solid structure. This step is where zirconia truly becomes ceramic. Without sintering, it's just powder. With it, we get a material that's stronger than steel at high temperatures and nearly as hard as sapphire. To further enhance its properties, zirconia is often stabilized with small amounts of yttria, Y2O3, or magnesia, MgO. These stabilizers keep the crystal structure in its toughened phase even when cooled, preventing cracks and improving durability. The result is what we call yttria-stabilized zirconia, or YSZ, one of the most advanced ceramics known today. It's this stabilized form that becomes the foundation for everything from turbine coatings to dental restorations. Here you can see YSZ in action. On one side, a dental lab is using CAD/CAM technology to mill zirconia crowns, and on the other, turbine blades are being coated with the same ceramic material. YSZ is unique because it combines metal-like strength with the temperature resistance of ceramics. In jet engines, it acts as a heat shield. In solid oxide fuel cells, it enables efficient energy conversion. And in dentistry, it's biocompatible, lifelike, and long-lasting. Few materials can cross from aerospace to healthcare this seamlessly. After sintering, zirconia parts go through finishing, the stage that perfects both performance and appearance. The image here shows polishing of a zirconia crown, but similar processes happen in aerospace and manufacturing. Finishing involves a combination of grinding, polishing, and glazing. Grinding ensures exact dimensions and removes any surface irregularities caused during sintering. This is especially critical for components like valves or implants, where tight tolerances mean the difference between performance and failure. Polishing follows next. Using diamond abrasives, technicians smooth the surface until it's mirror-like. This doesn't just improve appearance, it also reduces microscopic flaws that could lead to cracks under stress. In dental applications, zirconia crowns are stained and glazed before their final firing. The glaze gives them a natural enamel look while sealing the surface from bacteria and wear. In industrial uses, some parts undergo thermal shock testing, wear analysis, or coating adhesion tests to confirm quality. Others are laser inscribed with traceability codes for quality assurance. Here is a side-by-side comparison of zirconia's strengths and challenges. A realistic look at why it's both a marvel and a challenge for engineers. Zirconia's advantages are well known. It's incredibly tough for a ceramic, resists corrosion, and stays stable even above 2,000 degrees Celsius. Its biocompatibility also means it's safe for implants and medical use. And since it doesn't conduct electricity, it's ideal for insulating or energy conversion applications. But let's dig deeper into the challenges. The first is cost. The refining and sintering stages require enormous energy, especially when high purity and consistency are required. That's why zirconia products often cost more than traditional ceramics or metals. The second challenge is brittleness. Even though zirconia is tougher than most ceramics, it can still fracture under sharp impact or tensile stress. Researchers are tackling this through transformation toughening, where controlled crystal phase shifts absorb energy instead of cracking. Finally, there's energy intensity. High sintering temperatures and long cycle times contribute to the carbon footprint. But emerging solutions like microwave sintering, spark plasma sintering, and 3D printing of zirconia powders are showing promise for reducing costs and environmental impact. Despite these challenges, zirconium ceramics continue to evolve, proving that even the toughest materials can be refined for a more efficient and sustainable future. Zirconium represents the perfect blend of natural materials and human ingenuity. Its ability to withstand heat, corrosion, and time itself ensures its place at the core of future technologies in energy, aerospace, and medicine alike. Here are the references used throughout this video.